Imagine you're in a lush rainforest, the air thick with humidity and mystery. Deep in this tangle, a chemist named Paul Dewick is tracing the footsteps of nature's master chemists, enzymes sculpting molecules that heal, harm, or inspire. But how exactly does a simple plant cell spin out powerful medicines like morphine or aspirin? That's the story Medicinal Natural Products dares to unravel, one biosynthetic pathway at a time. Every drug in your cabinet started as a natural product. But what's the secret crafting process behind these molecules? Let's dive into the backbone of biosynthesis, where nature's blueprints come alive. Back in Chapter 2, Dewick introduces secondary metabolism, the metabolic rebels that don't directly fuel life but produce compounds like alkaloids and phenolics. Unlike primary metabolism, these molecules aren't for everyday survival but defense and attraction. Think of them as nature's secret stash of chemical weapons and love potions. The acetate pathway is like an industrial factory built inside cells. It synthesizes fatty acids and polyketides by snapping together small building blocks like Lego bricks acetate units. Imagine a train adding carriages, each one a carbon fragment, forming complex chains that later fold into life-saving drugs. Once you know the pathways, you see drugs in a new light. Aspirin, morphine, even antibiotics are biosynthetic triumphs, nature's craftsmanship retooled by humans. Dewick highlights how understanding these sequences enables scientists to engineer better medicines from natural templates. Some molecules don't just heal, they dazzle with their chemistry. The Shikimate pathway is a botanical wizard's workshop, crafting aromatic amino acids, the precursors to vital medicines. In Chapter 4, Dewick zooms in on the Shikimate pathway, plants' exclusive shortcut to aromatic amino acids like phenylalanine and tryptophan. These aren't just building blocks. They're the backbone for many pharmacologically active compounds, including the anti-inflammatory salicylic acid. Picture the Shikimate pathway as a delicately choreographed dance. Each enzyme is a dancer, handing off a transformed molecule like a baton. Molecule A twists and folds, becoming molecule B, then molecule C, culminating in that distinctive aromatic ring structure, the hallmark of many natural products. Why does this matter? Because those aromatic structures serve as scaffolds for drugs treating fever, pain, and even cancer. The more we decode this chemical choreography, the better we get at borrowing nature's tricks to develop targeted therapies. Alkaloids are the headline makers: morphine, quinine, caffeine, all born from specialized biosynthesis. But what makes their creation so fascinating and medically vital? Dewick tells us about the morphine saga, how the opium poppy's cells turn simple amino acids into a complex, potent painkiller. It's like a tiny chemical factory where over 20 enzymes carefully tweak molecules until they produce morphine's signature structure, with its potent effects celebrated globally. Think of enzymes here as master sculptors. They don't just build molecules, they carve them into forms that fit biological targets perfectly, like a key into a lock. Each enzyme's specificity ensures the molecule's shape matches receptors to produce the desired pharmacological effect. With the biosynthetic pathways mapped, scientists can now tweak these processes, creating analogs with fewer side effects or making production more sustainable. That's a game changer, moving from nature's gifts to tailored, precision medicines. That rainforest chemist Dewick imagined, he's showing us that every medicine began as a whisper in nature's complex biosynthetic language. Next time you pop aspirin or sip coffee, remember, you're embracing an ancient molecular tale crafted by enzymes, cells, and evolution. Try this. Next time you touch a plant or pill, pause and wonder about its secret biosynthetic journey. It's not just chemistry, it's nature's masterclass. Subscribe for more book summaries like this one.